Have you ever looked at a chemical formula and felt like you were trying to read a secret language? Well, today we're going to crack that code. And don't worry, we're tossing the boring textbook stuff out the window. Think of this more like a fun decoding exercise. By the time we're done, you'll basically be fluent. Okay, so look at this. H2O and H2O2. They look almost the same, right? Just one little number is different. But H2O, that's water. You know, the stuff we need to live. H2O2, that's hydrogen peroxide. Yeah, definitely not something you want to drink. That one tiny atom changes everything. And that right there is why learning this chemical code is so incredibly important. It's wild, isn't it? That one single extra oxygen atom makes a world of difference. And it's all communicated through this chemical language. So today, that's what we're going to do. We're going to learn the grammar, the vocabulary, everything you need to know to read and write in the language of molecules. So where do we start? Well, before we can even begin to read the code, we've got to understand why it exists in the first place. I mean, why do atoms even bother forming these partnerships? It really all boils down to one simple, fundamental need: sharing. And the secret sauce here is something called a covalent bond. It sounds kind of technical, but all it is what happens when two nonmetal atoms team up and agree to share electrons. And I really want you to focus on that word, share. This isn't about one atom stealing from another. It's a true partnership, and it's a partnership that makes both of them way more stable and happy. Let's look at our old friend, water. You see that big oxygen atom in the middle? It's sharing its electrons with those two smaller hydrogen atoms. By doing this, everybody gets what they need to feel stable and complete. It's like a perfect, tiny little team working together. Now, sometimes that partnership is super straightforward. Check out these two fluorine atoms. Each one just needs one more electron to feel whole. So what do? They each put one in the middle to share, and boom, they form a single, neat little bond. It's a simple, one-for-one deal, nice and easy. But other atoms are a bit more, let's say, needy. Take oxygen. Oxygen atoms each need two extra electrons to be satisfied. So when a couple of them pair up, sharing just one pair of electrons isn't going to cut it. They have to share two pairs. And that creates a much stronger connection, which we call a double bond. Okay, so we've got the why down. We know why atoms want to partner up. It's all about stability. Now let's dig into the how. What are the actual rules of engagement here? You'll be happy to know there's a real system to it, and it's actually pretty straightforward. The big rule we need to know is something called combining capacity. And I know that sounds a little intimidating, but trust me, it's not. All it is a number that tells you how many bonds an atom needs to form to become stable. You can think of it like how many hands an atom has available to hold hands with other atoms. And check this out. Here's the ultimate cheat sheet. You can see that carbon, for example, needs to form 4 bonds. Oxygen, which we just talked about, needs 2. And then you have guys like hydrogen and fluorine that only need 1. This little table right here, this is basically the key that lets you predict how all these different partnerships are going to work. Okay, now I want you to meet a very special group of elements. These 7 are, well, they're super codependent. They're so social, they absolutely cannot exist on their own out in nature. They're always paired up, usually with their own identical twin. And there's a great little mnemonic to remember them. Hoff, Bryn, Cole. Kind of sounds like a funny name, right? Hoff, Bryn, Cole. And here they are, all laid out. This means you're never going to just find a single oxygen atom, an O, just floating around by itself. Nope, it's always going to be O2. You'll never find a lone hydrogen, H. It's always H2. These 7 are basically the inseparable power couples of the chemistry world. All right, we've got the background info, we know the why and the how. So now it is time for the main event. We are going to actually start reading the code. This is the part where you become a chemical translator. Every good code has a key, right? A way to translate it. Well, for molecular compounds, this is it. These Greek prefixes, they tell you exactly how many of each atom you're dealing with. Di means 2, tri means 3, tetra means 4. You get the idea. This is your brand new vocabulary list. And just like any language, there are a couple of super simple grammar rules to follow. Rule number 1, if there's only one of the very first atom, you just drop the prefix mono. It's just implied. And rule number 2, the ending of the second element's name always changes to "ide." That's it. Just 2 little rules. Okay, let's try one out. SO3. So first element is S, which is sulfur. There's only one of them, so we just say sulfur. Remember rule 1, no mono on the first one. Easy. Second element is O, oxygen. And look, there are 3 of them. So we grab the prefix for 3, which is tri. Then we apply rule 2. Change the ending of oxygen to "ide," so it becomes oxide. Now just stick it all together. Sulfur, trioxide. Boom, you just read chemistry. Let's do another one to super quick. Let's say you have a molecule with 2 nitrogen atoms and 4 oxygen atoms. Okay, what's its name? Well, 2 nitrogens, that's dinitrogen. 4 oxygens, the prefix is tetra. Change oxygen to oxide, so tetroxide. Put them together, dinitrogen tetroxide. See? You're already getting the hang of this. It's like a pattern. Now, here's the really cool part. Once you know how to read the code, you automatically know how to write it too. The whole process just works perfectly in reverse. Come on, let's try it. Okay, let's work with the name dihydrogen monoxide. First part, dihydrogen. Di means 2, and hydrogen is H, so that gives us H2. Second part, monoxide. Mono means 1, and oxide comes from oxygen, symbol O. So we have O1. Now just combine them, H2O1. And we usually drop the 1, so H2O. And there it is, that super long, complicated sounding name, dihydrogen monoxide. It's just the proper, systematic name for good old water. How crazy is that? You've known its formula your entire life, and now you know where its real name comes from. It's a pretty cool aha moment when you see how the code works. And just like that, you've basically learned the fundamental grammar of molecular compounds. Seriously. You're not just staring at a jumble of letters and numbers anymore. You're actually reading a language. So let's do a super quick recap of the rules, just to lock it in. Think of this as your personal chemistry codebook. First, you use those prefixes, mono, di, tri, to count up the atoms. Second, you always skip mono for that first element. Third, you change the ending of the second element to "ide." And if you need to write the formula from a name, you just do the whole thing in reverse. That's literally the entire system. You know, when we started, you were probably just looking at a random collection of letters and numbers. But now, you see a language. You see the rules that govern how atoms build, well, everything around us. You've officially unlocked the code. So the only question left is, what are you going to decipher next?